Welcome back. So as promised, we're gonna move into the ideal gas law. And what is that? What is the ideal gas law? The ideal gas law is nothing more than a formula that assumes that a gas is behaving under ideal conditions, which are pretty close to the conditions that we usually have, room temperature, 1 atmosphere, and so on. So most of the gases follow that. So the ideal gas law is PB equals nRT. Notice that there's no P1 or B1 because this is not longer before and what happens after we change something. This is right here, right now. If the pressure is so much and the volume is so much and the temperature is so much, how much gas do I have? And what is R? R is what we call the gas constant. This number needs to be there for this to make sense. So the R constant for the ideal gas law is going to be 0.08206 liters times atmospheres over moles times Kelvin. So the R constant is going to be that value when we're dealing with the ideal gas law. There's another R gas constant that is 8.31 joules divided by moles times Kelvin. But if you remember from previous chapters, joule is a unit of energy. So whenever we are dealing with energy and you see the R constant, that's the one you use. On our particular case, we're not dealing with energy. So this is the R constant that you are going to need. The one with pressure, volume, and temperature and amount. Therefore, they are constant for the ideal gas law. So like I said before, this formula allows you to calculate here and now situations given 3 of the variables. And this formula is extremely important because let's say that you have a metal container made out of thick walls, and if we're dealing with gas, we're going to have a gauge that tells you how much gas you have, and you have so much gas there, so that would be N. The volume is given by the space it takes, so that would be your volume. And let's say there is a 25 degrees Celsius or 298 kelvins, that will tell you how much the pressure is. So you can calculate the pressure based on those conditions. And if you bought this container and the manufacturer told you do not exceed 3 atmospheres, it would be super important for you to know the maximum temperature that will give you that value, or even how much gas you can put in there. So like I mentioned before, the ideal gas law is used by engineers, by medical technologies, and all that to be able to know the limitations of the system they have. So let's do a problem with it. What is the pressure? So we looking, remember there's no P1 or P2, so we're just looking for the pressure. What is the pressure in millimeters of mercury? Millimeters of mercury. So what is the pressure in millimeters of mercury? The amount equals 0.0115 moles of helium. And we have a volume of 214 milliliters and a temperature of 45 degrees Celsius like any other gas law, it has to be Kelvin. So we're gonna change it to Kelvin, and that's gonna be 318 degree Kelvin. So the ideal gas law, since you don't see initial or final, this is not P1, B1, this is ideal gas law. There's no initial, there's no final. There's only one condition. So PB equals nRT. We're looking for the pressure, so that's what we're looking for. So that's the one we want to leave by itself. So we're going to leave it by itself by dividing by B on both sides. So when we do that, the B cancels, so we can take it out. And this is the formula we're going to use. P equals nRT over B. So P is going to equals the amount of moles. The moles is 0.0115 moles. Make sure that you put those units. Those are going to be extremely important. The R is 0.08206 atmospheres liters over moles Kelvin. And we're going to multiply that. So let me do something over here. So we're going to multiply that by the temperature, and the temperature is 318 Kelvin. So that's going to be our pressure divided by the volume, and the volume is 214 milliliters. So before we do anything else, let's check the units. So Kelvin, cancel with Kelvin, moles, cancel with moles. However, we have liters and milliliters. So we have to fix that. The units have to be the same. So the R values tells you the unit that you're gonna need. Remember, the R is given on atmospheres, in liters, and so on. So we cannot use 240 milliliters. We're gonna have to change that to liters. And that's gonna be 0.214 liters. So we went from liters to liters. Now the liters cancel with the liters. The only remaining unit is atmosphere, which is pressure. So we're looking for pressure. So let's do this problem. Let me go ahead and clear the screen a little bit. So now that we have that, it's just a matter of putting it on the calculator. So we're gonna have 318 times 0.0115 times 0.08206 divided by 0.214, and that's gonna give us 1.40 atmospheres. But the problem is asking for milliliters of mercury. So we take our atmospheres. We're going to be looking for millimeters of mercury, which means I do not care about the atmospheres because I'm looking for the milliliters of mercury. And I know that 1 atmosphere equals 760 millimeters of mercury. So therefore, 1.40 times 760 divided by 1 equals 1,066 millimeters of mercury. So that's how we use the ideal gas law. So once more, what's important on the ideal gas law? All the units have to cancel except the one you're looking for. That means that if you have liters and milliliters, one of those has to change to the other so you can cancel it. The R uses atmosphere, So if you're using pressure, it has to be in atmospheres, and so on and so on. So with that said, you should be able to work these three problems. So you can practice with the ideal gas law. Let me see if there anything that any hints that I need to give you. First one is straightforward. Second one is also straightforward. Third one, your pressure is on pounds per square inch, so make sure you change that to atmospheres. You know that all temperature has to be on Kelvin, so change that to Kelvin. And besides that, everything is straightforward. So really, a really super important formula, really easy to use, as long as you remember how to solve for x. And x is going to be whatever you're looking for. It could be pressure, it could be volume, it could be temperature, or it could be the amount. It cannot be R because R is a constant. And you know the value, 0.08206 atmosphere liters over mole Kelvins. And always, always write down your units when you're doing these problems. So let's do another one. A sample of gas has a mass of 38 milligrams. So the amount is 38.8 milligrams. And it says a sample of a gas, so we don't know what it is. We just know it's a gas. Its volume equals 224 milliliters. But I know if I'm dealing with the ideal gas law, I know it has to be in liters, so I'm going to change it to liters right away. And the temperature is 55 degrees Celsius, which I know it has to be on Kelvin. So 55 plus 273 is 328 Kelvin. So as you practice, those are things that you say, okay, it has to be Kelvin, it has to be liters. And the question is, find the molar mass. And PV equals nRT. This is pressure, this is volume, this is moles, this is the gas constant, and this is temperature. I do not see molar mass anywhere. So there's a problem there, right? Well, not really, because you already are about 11 weeks onto this course, so you know that the mole is nothing more than mass divided by the molar mass, right? So it's hiding, so let's rewrite it. PB equals moles, which is mass over molar mass times R times T. So we are solving for molar mass. So let's leave it by itself first. So I'm gonna divide by RT on both sides. That means that cancels, so I can get rid of it. So there's no need for a parenthesis anymore. And now I want to leave molar mass by itself. So what I'm going to do, what I like to do in this case, what I'm looking for is a denominator. I want it to be on top. So I'm going to flip everything around. RT over PB equals molar mass. So that's an acceptable trick over mass. So what I did, I flipped everything around so that what I'm looking for is on the top now. And now I just need to get rid of the mass. So I'm going to multiply by mass on both sides. That way I can cancel my mass, so I can get rid of it. And now I have exactly what I need. I did the math on it, so exactly what I need is going to be this. The mass is is 38.8 milligrams multiplied by R. R is 0.08206 liters times atmospheres over moles times Kelvin, multiplied by the temperature. The temperature is 328 Kelvin. So I did the top portion, I did all of that. And we're gonna divide this by the PV. Pressure is 886 torrs. That's right there. And the volume is 0.224 liters. And that should give me my molar mass. So my molar mass, which is what I'm looking for, is that. So before I do any calculation, let's look at the units. Kelvins cancel with Kelvin. Liters cancels with liters. So the only thing I have remaining now is milligrams, moles. So mass over moles, that would be molar mass. So I want to keep these two. However, I need to get rid of the atmospheres and they're not the same. But I know that 186 torrs can be converted to atmospheres by 1 atmosphere equals 760 torrs. So all I have to do is divide 86 torrs by 760 torrs. And that will give me atmospheres. So that number, once I cancel the torrs, those are gonna be atmospheres. So atmosphere would cancel with atmospheres, and that should be it. So 38.8 milligrams multiplied by 0.08206 multiplied by 328 divided by, I put this on parentheses, divided by 886 divided by 760, close parentheses, and all that divided by 0.224. That's gonna give me 3,999 milligrams per every 1 mole. And you will say, wow, that number looks super huge for molar mass. And yes, it's huge because we're dealing with milligrams, and you used to see it on grams per moles. So let's change that to grams. So we're just gonna divide by 1,000. So 3.999 grams per every 1 mole. So that's the molar mass of that gas. Basically 4, right? So that's helium. So based on the molar mass, we know that we're dealing with helium. So isn't that important? If you happen to go to a place where there's been an accident and you don't know what gas is there, you can get a sample, you can put it on a container, get the pressure, get the temperature and all that, and you can find the molar mass. And you can say, everybody can go in there, it's safe enough, you're only gonna be talking funny for a while, as long as there's oxygen available, right? So that's how we can use the ideal gas law to even go further and allow us to find molar mass by knowing that mole is nothing more than mass divided by molar mass. So we are expanding the formula a little bit more. So make sure you practice that. This is a very important skill. So you can practice with that. As always, I don't have to mention it, but let's say once more, show your work. And you're doing just what we just did. Do not just copy what we did. Make sure that you can work through it and get your knowledge. So if I ever show you the question a little bit different, you will know how to do it. And we got something more about ideal gas law. What about when you have a problem like this? Calculate the volume. So we're looking for the volume of each one of these gases at STP conditions. What is that? What is STP conditions? Well, let me tell you. STP conditions are going to be a standard, temperature, and pressure. So what this problem is telling you is that this is going to be at this, as what we know at the standard temperature and pressure. For gases, the standard temperature is going to be 0 degrees Celsius, which is another way of saying 273 Kelvin. By the way, sometimes you're going to see, for more precise work, you're going to see 273.15 Kelvin. So make sure you use whatever Alex is asking you to use when you do the problems in Alex. And the pressure is just going to be the standard pressure, the pressure of this planet, which is 1 atmosphere. So every time you hear STP conditions, remember that the temperature is 273 Kelvin and the pressure is 1 atmosphere. So this problem is giving us that information. It's telling us find the volume when the temperature equals 273 Kelvin, the pressure equals 1 atmosphere, and for the first one, the moles equals 1.0 mole. So let's do that. So PV equals nRT. There's no before and after, so it gotta be the ideal gas law, right? We're looking for volume, so we get rid of the P on one of the sides. That leaves the V all by itself. So that's what we're gonna use. So let's do that. So volume equals the moles, which is 1.0 mole. The R is 0.08206 atmospheres, liters, moles, Kelvin. The temperature on this case is 273 Kelvin. And the pressure is 1 atmosphere. When we do that, our volume is going to be 1 times 0.08206 times 273 divided by 1 equals 22.4 liters. Okay, so let's do the second one. Now that we know that the formula that we're using, I'm just gonna leave that one there and just change whatever I need to change. So we did the first one. The second one is nitrogen. So the first one was chlorine. The second one is nitrogen. And we have 1 mole, so that's already there. The R is there. The temperature is there. So we're gonna get 22.4 liters. Let's do it more challenging. Let's do helium now. And we got 1 mole. So we got 1 mole. We got R. We got temperature for STP. And it's also 22.4. Do you notice the trend? It doesn't matter what gas we're using. If you have 1.0 moles at STP condition, the volume is always 22.4 liters. So this is gonna make our life so much easier. This tells us, you know what? You really don't have to use the ideal gas laws for these problems. If I tell you that this is STP conditions, all you have to do is use this equality with dimensional analysis. So let's do the last calculation so you can see what I'm talking about. So we're not even using the ideal gas law anymore. As long as you tell me that we're dealing with STP conditions, I know that any gas will take 22.4 liters when we only have 1 mole of the gas. But what if we have 27 moles of methane, for example? Well, we know that methane doesn't, it's not important at all. At STP conditions, we don't care about what gas we're talking about. We only know that 1 mole of any gas is always 22.4 liters. So we can use that as a conversion factor. And all we have to do is multiply those values. 27 times 22.4 divided by 1, that's going to be 604.8 liters, which makes sense. If 1 mole of any gas takes 22.4 liters, then 2 moles should be the double, right? Avogadro's law. So 44.8, 3 moles is going to be 3 times that. So 27 moles is going to be 27 times 22.4, because it's that much for every 1 mole. So that's the important part here. If you're dealing with the standard temperature and pressure, which are 273 Kelvin and 1 atmosphere, there's no need to plug it into the ideal gas law to find what you're looking for. Just use dimensional analysis with that conversion, and you will be okay. You don't even have to use the ideal gas law because it's already been used to create that number. And with that, you should be able to do these problems. Remember, we're dealing with moles, right? So if your problem does not have moles, imagine what you had to do first. So you can use the conversion factor, 1 mole equals 22.4 liters. And once you do that, we can say that you have enough experience, pending more practice in Alex, to use the ideal gas law, which is going to be what we're going to use when we come back to do Dalton's law, which is derived from the ideal gas law, and to ultimately do a stoichiometry later. So until the next time, let's continue thinking about the ideal gas law.